Chapter 15. Semiconductor electronics. In semiconductor electronics, the materials which have conductivity and resistivity in between conductors and insulators are called semiconductors. Those materials which have their conductivity and resistivity, the conductivity and resistivity of those materials which lies somewhere between conductors and insulators, they are called semiconductors. Means semiconductors are not completely conductors, they are not completely insulators. When some conditions are being applied on them, then they behave like conductors, and without those conditions they behave like insulators only. Now the example of semiconductors are silicon and germanium. Now let us discuss about energy band theory of solids. Energy band theory of solids. Energy band theory of solids. According to Bohr's theory, there are well-defined energy levels of electrons in an atom. If large number of atoms are brought close to one another to form a crystal, they begin to influence each other. Due to this interatomic interaction, there is no modification in the energy levels of the electrons in the outer shell, but there is a considerable modification in the energy levels of the electrons in the outer shells. So what is this energy band theory? We know about the energy levels, but we don't know about the energy bands. What is this? What are these energy bands? Look, as we have one atom, so in one atom there is a nucleus. So nucleus is here. This is first energy level. This is second energy level. And like that we have third energy level, fourth energy level. So this is about only one atom. So a material consists of so many atoms, infinite number of atoms. Okay, so if I talk about a few atoms, then those few atoms will interact with each other. They will interact with each other, and when they are brought close to each other, due to when they are brought close to each other due to some processes, due to some procedures. So some procedures are being done to bring these atoms close to one another. When these atoms are brought close to one another, then these energy levels actually touch each other. These energy levels interact with each other like this. These energy levels interact with each other like this. And when they interact with each other, then what happens? One energy level comes close to another energy level, third energy level comes close to fourth energy level, and like this. There are so many electrons. So when these energy levels come close to each other, then they form energy bands. And there are two types of band. when we talk about energy band theory, there are two type of bands. One is called conduction band and one is called valence band. So when this outermost shell, example, in this case, this is nucleus, and the outermost shell is second shell, and in this other atom the outermost shell is second shell. So when this outermost shell interacts, means touches each other or collide with each other, then these outermost shells, the electrons in these outermost shells are called valence electrons. We know that the electrons in the outermost shells are called valence electrons. So when such type of valence shells are brought close to each other, then they form a band, and that band is called valence band. So we have two types of band. One is valence band, and another is conduction band. So any material will behave like a conductor if there are electrons in the conduction band, and if there are electrons only in the valence band, then that material will not behave like a conductor. So for a material to behave like a conductor, electrons will have to jump from the valence band to the conduction band. So this is all about band theory. Band theory means when we in any type of atom, in any element, when we bring together these small atoms, when small atoms comes together, then when valence band of one atom interacts with valence band of another atom, and that valence band of second atom interacts with valence band of third atom, valence band of third atom interacts with valence band of fourth atom, then they together form a dense band, and that band is called valence band. So valence band have plenty of electrons. It has so many electrons. And conduction band, generally in a semiconductor, conduction band do not have any electrons. When electrons from this valence band, they jumps to this conduction band, then a semiconductor starts behaving like a conductor. It means then it starts conducting current. Is this clear to you?
Yes, sir.
Okay. So do you have these notes with you right now? These notes, this one?
Yes, sir.
Okay. So this was all about first page. This graph, you need not to do this graph. Just leave this graph. This graph is not being asked in the exams. And then the next page, all the theory about this energy bands is written. This is also not required to be done. Okay. Now please come on to the third page. Come on third page. So this is VB. VB stands for valence band, and this is CB. CB stands for conduction band. Valence band VB, conduction band CB. Now the dotted line which I am drawing in this valence band, these are the energy levels. These are the circular energy levels, and circular energy levels, I am representing those circular energy levels by straight lines. Okay, Similarly, in the conduction band also I am drawing these straight lines, these dotted lines. It means that the inner energy levels which interact with inner energy levels of another atom, and that interacts with further another atom, then those inner energy levels come close to each other and they form conduction band. So what happens? Valence band is always filled with electrons. Valence band always have electrons, plenty of electrons. And conduction band do not have electrons. So valence band is filled. Filled means it is filled with electrons, and conduction band is empty. So if I say this, that conduction band is empty and valence band is filled, then it means that I am talking about an insulator. In an insulator, the valence band is filled and conduction band is completely empty. Okay. Now, difference between, onto the same page, page number 3, difference between this one. I'm coming on this topic, this one. Difference between metals or conductors, insulators and semiconductors on the basis of energy bands. Difference between metals or conductors, between metals or conductors, insulators and semiconductors on the basis of energy bands. On the basis of energy bands. So it is very simple concept. Let's discuss it. In conductors, the conduction and valence band partly overlap each other and there is no energy gap in between. In conductors, the conduction and valence band partly overlap each other and there is no energy gap in between. So the gap between valence band and conduction band, this gap is called energy gap, EG. This is called energy gap. So in case of conductors, this is conduction band. This is valence band. And in case of conductors, what happens in case of conductors? In case of conductors, this valence band actually overlaps. This valence band actually partly overlaps with conduction band. So this is called conductor. So when valence band and conduction band, they partly overlap each other, it means that electrons from the valence band, they get sufficient chance to move to the conduction band because there is partly overlapping. They partly overlap with each other. So this is valence band and this is CB. CB means conduction band. So they partly overlap each other. So that's why valence band that's why electrons from the valence band, they get sufficient chance to move to the conduction band and hence they constitute in electric current. So that's why they are called conductors, because they conduct electricity. Is this clear to you?
Yes, sir.
Okay. Next one. Next one, insulators. Insulators, again, we have this conduction band. And this is valence band. This is valence band. And there is a huge difference. There is a huge gap between conduction band and valence band. So the difference between, the gap between conduction band and valence band is called EG. Conduction band is CB, valence band is VB. The gap between both of them is called EG. And EG is generally greater than 3 electron volt. EG is greater than 3 electron volt. If the energy gap is this energy gap, what is the meaning of this energy gap? Is this distance? No, this is not distance. I am not talking about distance. Energy, actually distance is always there. The conduction band and valence band, they are separated by a small distance, but this is not distance. This is energy gap. Energy gap means 3 electron volt, means every electron from the valence band requires more than 3 electron volt of energy to jump to the conduction band. Is this clear? What is this EG? So this is this is about conductors, and this is insulators. Conductors, insulators. Now about semiconductors, let's move on to the next slide. Okay, now about semiconductors. In semiconductors, this energy gap is small. This energy gap is EG is less than 3 electron volt. So energy gap is small. Small energy gap means electrons from the valence band require very less energy. Energy is less than 3 electron volt to jump from this valence band to conduction band. So valence band is filled and this is empty. Conduction band is empty. Semiconductors. All right, is this clear?
Yes, sir.
Okay. Now next we have on the next page, onto the next page, we have intrinsic semiconductors. Intrinsic semiconductors. Intrinsic semiconductors. What is this? The purest form of semiconductors, the purest form of semiconductors which do not have any type of impurity is called an intrinsic semiconductor. I'm just reading it out from the notes. A pure semiconductor which is free from every impurity is called intrinsic semiconductor. Examples: silicon and germanium. The most commonly used semiconductors are these silicon and germanium only. So and both these elements, silicon as well as germanium, both these elements they have 4 valence electrons. Means they have they have 4 electrons in their outermost shell. So they form covalent bonds. Both of them are tetravalent. So how they combine with each other? Pure form of semiconductors without any impurity are called intrinsic semiconductors. The pure form of semiconductors are called intrinsic semiconductors, and examples are silicon and germanium. Silicon and germanium. These are germanium atoms. Germanium and germanium is also tetravalent. Germanium is also tetravalent. So tetravalent means it has, just like germanium has 4 valence electrons. Germanium has 4 valence electrons in its outermost shell. This is the electron dot structure of germanium. And the next germanium atom also has 4 valence electrons. So what happens? It shares this 1 electron with this neighboring germanium, and this neighboring germanium shares its 1 electron with it. Similarly, it shares 1 electron with this neighboring germanium, and it also shares its electron with it. This germanium, similarly, it shares 1 valence electron with the upper neighboring germanium atom, and upper one shares with it. Similarly, this germanium atom shares its electron with this neighbor, and this germanium atom shares with it. This germanium atom shares with this, and this germanium atom shares its electron with this. So in this way, this crystal lattice structure forms. This is intrinsic semiconductor, means purest form of semiconductor. Like this. So like this, a germanium crystal lattice structure forms. So this is all about intrinsic semiconductor. Both the atoms, I am reading the last line of this page, both the atoms, silicon and germanium, have 4 valence electrons. Have 4 valence electrons. The 4 valence electrons of a germanium atom form 4 covalent bonds by sharing the electrons of neighboring 4 germanium atoms. The minimum energy required to break a covalent bond is 0.72 electron volt for germanium and 1.1 electron volt for silicon. So the energy gap for germanium, energy gap for germanium is 0.72 electron volt, and energy gap for silicon is 1.1 electron volt. So energy gap for germanium and silicon, this is the difference. And I know that both are semiconductors, and in semiconductors we have energy gap always less than 3 electron volt. So for germanium, energy gap is 0.72 electron volt, and for silicon it is 1.1 electron volt. Both the cases, the energy gap is less than 3 electron volt. Now, next. When an external electric field is applied, these free electrons and holes move in opposite directions and constitute a current. The number of free electrons and holes are exactly equal in an intrinsic semiconductor. Now the question arises, what is this hole? When an electron leaves its place, when an electron jumps from one place to another place, then when an electron jumps from its place, then electron leaves that place empty, and that place is known as a hole. So this is an electron, and when this electron jumps like this from here to this place, then it leaves a hole here. Electron comes here and it leaves a hole here. And what was observed? It was observed that when electron jumps from this place, then it gets slightly attracted towards this place. And when this electron, when an electron gets attracted towards a place, then it is considered that this must be a positive charge. But it is not a proton, because proton comes out of a nucleus. So this is known as a hole, and his hole is necessarily a positive charge. This is hole. Why we have termed it like a hole? Hole is anything which is an empty space, and this empty space is created when electron jumps from its place, from electron's place to another place. So this is hole, this is positively charged, and this is electron, this is negatively charged. All right, is this clear to you till now?
Yes, sir.
Okay, and it has been observed that in an intrinsic semiconductor, the number of electrons and number of holes, they are always equal to each other. Okay, that is NE is equal to NH. Number of electrons is equal to number of holes. Next line. Also, the conductivity of intrinsic semiconductor is very low. Conductivity of intrinsic semiconductor is also very low. The hole is considered as an active particle in the valence band, having a positive charge equal to that of an electron. The hole is considered as an active particle in the valence band, having a positive charge equal to that of an electron. A hole has a positive charge equal to that of an electron. Now, the next topic is doping. Doping, D-O-P-I-N-G, doping. Doping. What is doping? Doping is a process of addition of a desirable impurity atoms to a pure semiconductor to modify its properties in a controlled manner. The impurity atoms added are called dopants. So why we add some impurity atom to a purest form of semiconductor? Because purest form of semiconductor do not provide conduction and insulation properties in a very controlled and very proper manner. So to control the conduction of a semiconductor, to control the insulation of a semiconductor, some impurity has to be added inside a pure semiconductor. And the process of adding some impurities to an intrinsic semiconductor is known as doping. So where these semiconductors are used, this silicon, this germanium, silicon and germanium, these semiconductors are used in making the motherboards and printed circuit boards of the mobile phones, laptops, and all the modern electronic gadgets. So in that, this silicon chip, you might have heard about it. Silicon chip or silicon motherboard, they are used in making computers, mobile phones, laptops, and all the new modern electronic gadgets. So why doping is done? Doping is done just to increase its conductivity when it is required. When we connect our mobile phone to a charging cable, then it becomes a conductor. It behaves like a conductor, and for that reason, it is specified in the user manual of every mobile phone that while your mobile phone is connected, while your mobile phone is getting charged, then during that time you please avoid to make a phone call to any person, because in that position, although some insulation pads are provided outside the packing of the mobile phone, uh, besides that also, sometimes some current may leak out of that mobile phone. So it is quite dangerous. It is quite dangerous at that time to put a conductor which is in conduction mode near your ear or touch your face. So while charging we should not use our mobile phone. Okay, so because during charging it behaves like a conductor, and when we remove the charging cable, then it behaves like an insulator. So this is the beautiful property of a semiconductor, that whenever we want, we switch it to conduction mode, and whenever we want, we switch it to insulation mode. Is this clear to you?
Yes, sir.
Okay. Doping of a semiconductor increases its electrical conductivity to a great extent. And methods of doping? Methods of doping are first is add the impurity atoms in the melt of semiconductor. Melt of semiconductor. Second, implant the dopant atoms by bombarding the semiconductor by bombarding the semiconductor with their ions. With their ions. And third, heat the semiconductor in atmosphere of dopant atoms. In the atmosphere of dopant atoms. Now, please move on to the next page of your notes. Now the next topic is extrinsic semiconductors. So these are the methods of doping. Add the impurity atoms in the melt of a semiconductor. In the melt of a semiconductor means semiconductor is now a little bit heated, and it is in its molten state. Then in that molten state, if we add some impurity atoms, then those impurity atoms get stuck inside the semiconductor and they becomes an extrinsic semiconductor. When we add some impurity to intrinsic semiconductor, then they become extrinsic semiconductor. Now, second is implant the dopant atoms by bombarding the semiconductor with their ions. So, implant the dopant atoms by bombarding the semiconductor with their ions. When we bombard means constantly hit the semiconductor with the ions of some impurity atoms, then also extrinsic semiconductor can be formed. Okay, and third is heat the semiconductor in the atmosphere of dopant atoms. Okay, and in the atmosphere of dopant atoms, if we heat the semiconductor, then semiconductor absorbs some impurity atoms and they become extrinsic semiconductor. Okay, now the next topic is extrinsic semiconductors. Can you wait for 2 minutes?
Yes, sir.
Okay, I'm just coming back. Okay. Now the next topic is extrinsic semiconductors are doped. Anusha, are you there? Are you there?
Yes, sir.
Okay. Okay. Extrinsic semiconductors are doped semiconductor. Extrinsic semiconductor, a doped semiconductor or a semiconductor with suitable impurity atom. A doped semiconductor, a doped semiconductor or a semiconductor with suitable impurity atom added to it is called extrinsic semiconductor. Extrinsic semiconductors are of two types, n-type semiconductor and p-type semiconductor. So extrinsic semiconductors are of two types, n-type and p-type. N-type means negative type, p-type means positive type. N-type semiconductor. N-type semiconductor. When a pure semiconductor of silicon or germanium is doped with pentavalent atoms means an atom which has the valency of the which have 5 valence electrons. 5 means penta, so pentavalent atoms which have a valency of 5. So when a pure semiconductor of silicon or germanium is doped with pentavalent atoms which have 5 valence electrons like phosphorus, arsenic, antimony or bismuth, then it is called n-type semiconductor. The 4 of the 5 valence electrons of the impurity atoms will form covalent bond with the adjoining 4 atoms of the silicon, while the 5th electron is free to move. Thus, each impurity atom added donates 1 free electron to the crystal. These impurity atoms are called donor atoms. So, if we have a structure like this, 1, 2, 3, 4, 5, 6, 7, 8. Silicon, 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 silicon. Okay, and a pentavalent impurity atom is just like phosphorus or arsenic or antimony or bismuth. So if I add this arsenic, then arsenic has 5 valence electrons. It has 5 valence electrons. So this silicon is making a bond with this silicon, this is making with this is making with this is with this. This silicon is making a bond with this. Okay, it means that one electron, silicon is sharing sharing its one electron with this arsenic. This arsenic is sharing its one electron with this silicon. In the same way, this silicon is sharing its one electron with this, and this arsenic is sharing its one electron with that. In the same way, arsenic is sharing its one electron with silicon, and silicon is sharing one electron with this. Arsenic is sharing one electron with this silicon, and silicon is sharing its one electron with this. So arsenic has shared 1, 2, 3, 4. Arsenic has shared 4 electrons, but arsenic had 5 electrons because it is a pentavalent atom. So it had 5 electrons. So 5 electrons means 1 electron is still vacant. 1 electron is still free to move. So when we have in any type of crystal structure, when we have free electrons, then free electrons, actually electrons have a tendency to move here and there, and the movement of free electrons constitute a current. So just to increase the conductivity of a semiconductor, this impurity atoms, this doping needs to be done. So this one structure, this one lattice has one free electron. Similarly, another lattice will have another free electron. Another lattice will have another free electron. So we don't have so many free electrons, but yes, we have some free electrons. So a little bit conductivity is this silicon crystal lattice is having, and this arsenic is contributing some few more electrons. It is contributing few more electrons which are free to move, and the free moving electrons actually increases its conductivity. Is this clear to you?
Yes, sir.
Okay, so now now because some extra electrons are being added to the crystal structure of silicon, some extra electrons are being added. It means some extra negative charge is being added. Negative means n type semiconductor. That's why this type, when we add some pentavalent impurities, then this type of semiconductor is known as n type semiconductor. Is this clear to you?
Yes, sir.
So that's why in n-type semiconductor, electrons are called majority charge carriers. Majority charge carriers means in a semiconductor, holes also move from one place to another place to carry current. So holes also carry current, electrons also carry current, but in n-type semiconductor, when we add one pentavalent impurity, then what it does, it actually increases the number of electrons in the structure, in the crystal of the silicon. So that's why electrons are in majority. That's why electrons are called majority charge carriers in n-type semiconductor. Electrons are majority charge carriers while holes are minority charge carriers. Minority charge carriers. Okay. Next is p-type semiconductor. So as the name suggests, p-type means positive charge, positive type semiconductors. P-type semiconductor means positive type semiconductor, and how this type of doping is done. In p-type semiconductor, one trivalent impurity is being added to the crystal. Trivalent impurity is being added to the crystal. So germanium. Now let's make a germanium crystal lattice. We can do it with silicon also. Let's do it with germanium. Trivalent impurity, trivalent atom is indium. Trivalent means an atom which has a valency of 3, which has 3 valence electrons in its outermost shell. It has 3 valence electrons. So 1 electron it shares with this germanium, 1 electron it shares with this germanium, 1 electron it shares with this germanium. So it has only 3 valence electrons. valence electrons, 3. But still in the inner shells it has some electrons. So one electron from the inner shell will go to this germanium, but we are not able to locate that, because in electron dot structure we locate only the outermost electrons. Outermost electrons are 3. So I have located this electron, and this electron. So the next electron leaves a vacant place here. Vacant place means it leaves a hole here, and one electron is being shared with this indium. So it leaves a hole here. Hole, do you understand what is this? This is positive charge. And in the same way, in the entire crystal lattice, like 1, 2, 3, 4, 5, 6, 7, 8. 8 germanium atoms. In 8 germanium atoms, and in 8 germanium atoms there is one indium atom. So this is forming a small lattice. This is forming a little structure, a basic unit structure of this germanium lattice. So we have so many number of germanium lattice in the entire germanium board or silicon board. So here these holes are majority charge carriers. This positive charge is majority charge carriers. So p-type semiconductor, the 3 valence electrons of the impurity atom will form covalent bonds with the adjoining 3 atoms of germanium, while there will be one incomplete covalent bond with a neighboring germanium atom. This deficiency of an electron creates a hole. The trivalent atoms are called acceptor atoms, and the conduction of electricity occurs due to the motion of holes, that is positive charges. So the resulting semiconductor is called p-type or acceptor type semiconductor. So here electrons are minority charge carriers, and holes are majority charge carriers. Is that clear?
Yes, sir.
Okay. Moving on to the next page, we have difference between intrinsic semiconductor and extrinsic semiconductor, and difference between n-type and p-type semiconductor. This one. So this is very much important. This one, difference between intrinsic and extrinsic semiconductor and n-type and p-type semiconductor. You have to learn it. Okay. The next topic is p-n junction. Actually, this is a big topic, so we will do it in the next class. Okay, Anusha? And if it is possible for you, can I take a class tomorrow?
What time, sir?
You tell me, as per your convenience.
Can you take it next week? Because on Monday I have an exam.
Okay. No problem. If you have time, you decide.
My winter break starts on the 13th. So I can take any time, every day.
Okay.
As much as you want.
Okay, no problem. Then we can start taking these classes from Monday. Okay. All right, Anusha.